First question is, which are the important formulas for the heat conduction through extended surfaces with condition fin with insulated end? Second question, solve one problem with condition fin with insulated end. We will understand some important formulas for the heat conduction through extended surfaces, that is fins. We will consider the first type, that is the fin with insulated end. Now here is the diagram. We will first understand the notations. So this is the extended surface is known as fin, which is having length L. Now what is the temperature at the base of this fin? So this base of the fin temperature is TO and the surrounding temperature is known as TF. So suppose we will consider the surrounding there is air, that means fluid, then it is having convective heat transfer coefficient, that is H. So we will also mention here, that is the convective heat transfer coefficient, that is H. Now we will understand how this heat is transferred along its length L through the process of conduction. So for that we will draw here one graph. On the horizontal line we will show the distance from the base of this fin towards the length L. So here is the distance x, and on the vertical line we will show the temperature. Now at the base there is the maximum temperature because from the base heat is transferred through the conduction process towards the tip of the fin. Now here the total length L. So we will draw here one vertical line for this length L. So I will draw here one construction line, that is in the form of dot. Now what is the surrounding temperature? So surrounding temperature is TF and which is constant. So we have to show here, that is the constant surrounding temperature TF. So I have shown here with the help of red marker. Now as the heat is conducted through the fin from its base to the tip of this fin, then its temperature is getting decreased. And here the type of fin is fin with insulated end, that this tip of the fin is insulated. So whenever the fin is insulated, that means there is no any heat transfer, or we can say temperature gradient is equal to 0. So at this end we can say that temperature gradient is equal to 0. Now we will show here the structure or graph of the temperature as it decreases along the length L. So I will show here. So here is the maximum temperature, that is temperature TO, and in this way the temperature is getting decreased. Now what is the temperature difference, that is TO minus TF. So this temperature difference we will consider here as a theta O. So I will show here this temperature difference with the help of the diagram. So this temperature difference is known as theta O, and in the formula we have to consider this theta O. Now we will consider the temperature at any point x for this fin. So we will consider any section. So I will consider randomly this section x. Now for at this section x, what is the temperature at this point, that is Tx. Then as we consider here, theta O is equal to TO minus TF. Then in the same way Tx minus TF is nothing but theta. So we will show here that I will extend this construction line. So here is the temperature Tx and here is the temperature Tf. So here this temperature difference is known as theta because here is the temperature Tx and here is the temperature Tf. Now we know that at the insulated end temperature gradient is equal to 0. So at x is equal to L, because here x is equal to length L. So at x is equal to L, d theta by dx is equal to 0. So this is the diagram for the fin with insulated end. and this diagram is important to solve the problem. So with the help of these notations and this structure, we are going to solve the problem which are under fin with insulated end. Now we will move to the first formula. So first formula is the temperature distribution equation. So what is the meaning of temperature distribution equation? So that is how to calculate the temperature at any section or at any point along this fin. That is the formula for the temperature distribution. But here we are not going to use direct temperature, but we are going to use the temperature difference. That is the temperature difference in between the surface or this fin and this surrounding temperature. So this terms of theta O or theta, we are going to use the formula. So what is this formula? So formula is temperature distribution equation theta by theta O. That is theta by theta O is equal to cos h m L minus x divided by cos h m L. Now what is this x? So x, that means any section, or we can say any point along the fin, and L, that is the total length of the fin. Now what is this m? So m is under root of Hp by Ka. Now what is this H? So H is the convective heat transfer coefficient. Then P is the perimeter of the fin, so that is also mentioned in the question. A is the area of this fin, so that is also mentioned. So here to calculate this, there is the effective area that is provided, that is mentioned in the question, and K, that is the thermal conductivity of the material, that is fin material. So that is also mentioned in the question. So with the help of all this information, we can calculate here the M. So it is easy for us to calculate this, the temperature distribution equation. So with the help of this equation, we can calculate the temperature at any point along the fin. Now we will move for the next formula. So next formula is for heat flow rate from the fin. So what is the heat flow rate? So heat flow rate, that is known as Q. So how to calculate this Q? So here is the formula. So Q is equal to under root of Hpka theta O tan H in the bracket M into L. So all this information is known, that is what is Hpka, then theta O, and then we have to take M with the help of this formula, and L is the length of the fin. Then we will move for the fin efficiency. So what is the meaning of fin efficiency? That is the actual heat flow divided by maximum heat flow, that is Q by Q max. So this is the formula. So with the help of this, we can calculate this efficiency. So how to calculate actual heat flow? So actual heat flow, that is the formula for Q, under root of Hpka theta O tan H ml. And how to calculate this Q max? That is the maximum heat flow. So to maximum heat flow, that means the surface, we have to use the area as a surface area of this fin. So HAF theta O is the formula. But what is AF? That is the surface area of the fin, that is nothing but perimeter of the fin multiplied by length. So we will transfer here AF is equal to P multiplied by L. And if we simplify this, so we have to remove this AF and P multiplied by L we have to put here. Then if we simplify this, then we will get tan H ml divided by under root of HP by KAL. So final formula to calculate neta, tan H ml by ml. Now we will understand the formula for fin effectiveness. So how to measure the effectiveness of the fin? So we have to compare the heat transfer. So what is the heat transfer from this fin surface, and if the fin is not available, then what is the heat transfer from the base of the fin? Then we have to compare this heat transfer. So how we can write? So it is the ratio of heat transfer from the fin surface to the heat transfer from the base surface in the absence of fin. So we know the formula for heat transfer from the fin surface, that we have already discussed, that is Q is equal to under root of HPKA theta O tan H ml. Now what is the heat transfer from the base surface? So that will depends on the area of base and then this theta O. So what is theta O? That is the temperature difference TO minus TF at the base. So fin is not available, so we have to take the parameters available only at base. So this theta O as well as area, so area at the base that we have to consider, and this H, that is the heat is transferred by this convection process, so we have to consider this convective heat transfer coefficient. So we will take HA theta O. Then if we simplify this, then theta O will be getting cancelled, and or then we will get the final formula tan H ml divided by under root of HA by Pk. So this is the formula to calculate effectiveness. Notation is epsilon. Now we will understand what is the relation in between this fin efficiency and fin effectiveness. So effectiveness by efficiency is equal to surface area of fin. So surface area of fin, that is perimeter multiplied by length divided by cross sectional area of fin. So cross sectional area, that means the area at the base available, so we can consider this as a cross sectional area. So we can take here P into L divided by A. So this is the relation in between effectiveness and efficiency.
Now we will read the given question. Consider a transistor idealized as a long cylinder of radius 1 mm and length 1.5 cm. On this, a sheath of 1 mm thickness with K is equal to 0.1 watt per meter Kelvin is put. Rating of transistor is 150 milliwatt, and if the transistor is to function properly, its surface temperature at radius 1 mm should not exceed 80 degrees Celsius. If ambient air is at 30 degrees Celsius with H is equal to 15 watt per meter square Kelvin, how much heat can be dissipated into the atmosphere by 3 brass leads with K is equal to 120 watt per meter Kelvin. Suppose we use circular wire leads of 0.3 mm diameter. What should be the length of these leads exposed to the atmospheric air?
Let us understand the given data with the help of diagram. Here is the front view and here is the top view that I have drawn. Now it is given that the radius of transistor, so radius of transistor is 1 mm, and over that transistor there is the layer of insulation sheath, and that is having thickness 1 mm. So in the front view we will show this transistor radius. So this is the center line which we have to draw, and the radius is 1 mm, and over that thickness of 1 mm for this insulation. So conductivity K for this insulation material is also mentioned. Now if we observe the top view, that is the circular cross sectional area. So this is the circular cross sectional area for this transistor, and this outer circle is for the circular cross section for the insulation material. So what is the radius R1? So radius R1, that is the radius for the transistor, that is 1 mm. So we will mention here R1 is equal to 1 mm. And how to calculate R2? So from the center line, the distance from this insulation material is 1 mm plus 1 mm, that is 2 mm. So R2 is equal to 2 mm. Now there is the conductivity K for the insulation material that is mentioned. Then the condition is given that we have to maintain the surface of transistor 80 degrees Celsius. So this is the surface of transistor 80 degrees Celsius. We will consider this temperature as a temperature T1. So we will mention here for this circle, here the temperature T1 80 degrees Celsius. Now the surrounding temperature is given 30 degrees Celsius, and the heat is transferred through the convection process, and convective heat transfer coefficient H is also mentioned in the question. So this temperature is nothing but temperature T2. So here is the temperature T1, here is the temperature T2, and the heat is transferred from this transistor surface towards the surrounding temperature. So what is this heat transfer that we have to calculate first? So if we observe, conductivity K is given, convective heat transfer coefficient H is also given. So we will consider here heat is transferred from this temperature T1 towards temperature T2. So here is the direction of the heat flow Q. Now we will first find out what is the resistance. So first there is the conduction process, conduction heat transfer process that is taking place. So resistance R1 is for the resistance for the conduction heat transfer. So we will mention here R1. And then after that, from this insulation surface there is the convection heat transfer process from this surface to the surrounding. So we will consider resistance R2 for the convection heat transfer process. So here is the resistance R2. Now the heat is transferred one after the other. So this is the pattern of the heat transfer. That is, first there is conduction process and after that there is the convection process. So we can say that R1 and R2 are in series, and this heat transfer is taking place in between temperature T1 and T2. So we will draw here electrical analogous circuit. So here is the resistance R1, then here is the resistance R2, and we will consider the temperature difference, that is T1 minus T2. Now we will find out what is the value Q, that is what is the amount of heat transferred from this transistor surface towards the surrounding. So we have formula, that is Q is equal to delta T by summation of R. So this delta T, that is the temperature difference T1 minus T2, and summation of R, that is R1 plus R2. So what is R1? So R1 is for the conduction process, and in between it is in between radius R1 and R2. So we have formula for the cylindrical structure. R1 is equal to ln R2 by R1 divided by 2 pi L K. So ln 2 by 1. So R2 and R1 both are in millimeter. So this millimeter is getting cancelled, and here the standard unit is meter. So we will use this value in millimeter because from numerator and denominator both the units are getting cancelled. Then 2 pi Lk. So 2 pi L. So L we have to consider this length in meter. That is 1.5 to 10 raised to minus 2 into K, conductivity 0.1. So which is equal to 73.54 Kelvin by watt. Now we will find out what is this R2. So R2 is convection heat transfer. For the convection heat transfer process, formula is 1 divided by H2 pi R2L. Now this outer surface of the insulation, which is having radius R2, is in contact with air, and here is the length 1.5 centimeter. So we have to use this formula. So H is given, so 15 into 2 pi into 2 into 10 raised to minus 3. R2 we have to use in meter, and L length is also we have to take in meter. So when we solve this, we will get 353.67 Kelvin by watt. Now we will take this summation of R, that is R1 plus R2, and delta T, that is 80 minus 30. 80 minus 30. So what is this value of Q? That is 0.117 watt. It is given that the 3 brass leads are provided over this transistor to dissipate the heat, and the diameter for this brass lead is given 0.3 millimeter, and we have to find out the length for this brass lead. Now we know that what is the radial heat flow. So radial heat flow, that is Q, that we have calculated earlier. Now we have to find out what is the heat dissipated by each brass lead. Now if we observe the question, then it is given that the rating of the transistor. So rating of transistor is 150 milliwatt, that is equal to 0.150 watt. So how to calculate heat to be dissipated by these 3 brass leads? So for these 3 brass leads, heat to be dissipated is equal to rating of this transistor minus radial heat flow, that is Q. So this 0.150 minus 0.117, which is equal to 0.033 watt. But this is heat to be dissipated by 3 brass lead. So what is heat to be dissipated by one brass lead? That is this answer divided by 3. So heat to be dissipated by one brass lead is equal to 0.011 watt. Now this is the heat that is getting dissipated by one brass lead. Now what is this brass lead? So this brass lead is nothing but the extended surface for the heat transfer. Now this is material used is brass and whose conductivity K is also mentioned in the question. So I will write here that conductivity K is also mentioned. Now we have to use the formula for the heat transfer through the fins, because we will consider this 3 brass lead as a fin and we have to find out what is the length for this fin. So how to calculate the heat transferred by the fin? So we have formula, that is heat is getting transferred by the fin, that is Q is equal to under root of HPKA theta O tan H ml. Now we will understand this formula. So H, that is the convective heat transfer coefficient. So this heat is getting transferred to the surrounding air which is having H, convective heat transfer coefficient. P is the perimeter. Now here diameter is given for the brass lead, that means this is the circular brass leads, and what is the perimeter for this circle? So perimeter of circle, that is pi d, that we have to use. Then K. So conductivity K for this brass material is also mentioned. Then A, area of this brass. So area of this circular section, area is equal to pi by 4 d square. So we have to use this formula. Then we will use theta O. So what is this theta O? That is TO minus TF. So at the base, that is here, at the base of this fin, what is the temperature? So surface temperature is given 80 degrees Celsius. And what is the surrounding temperature? That is 30. So theta O, that is 80 minus 30. Then tan H ml. So here M we have to calculate and L that we have to find out. So how to calculate the value of M? So M we have formula under root of HP by Ka. So under root of H 15 into pi d, that is pi multiplied by what is diameter 0.3 into 10 raised to minus 3. We have to use the standard unit, that is meter, divided by K. So K is given 120. A, area pi by 4 d square, that is pi by 4 into 0.3 into 10 raised to minus 3 bracket square. So if we solve this, we will get the answer 40.82. So with the help of calculator we can easily calculate this. Then we will put the value. So value of Q, that is known 0.011. Then under root of HPKA, that we have to write all the values into theta O 80 minus 30 and tan H ml. So M is 40.82 into L. So if we observe this equation, only one unknown term, that is L, and value of L is equal to 0.018 meter.